this is exactly not related to your course. But we will discuss some of the practical aspects. Practical design aspects. If you design an antenna, then some of the aspects we will discuss. बंद कर रही है बंद कर कर बंद कर म्यूट कर हाँ असला कर म्यूट करता कर so let us start with, suppose you are designing a dipole antenna, half-wave dipole antenna. So what is to be considered when you design a half-wave dipole antenna? We have studied in the book, you have studied about half-wave dipole antenna in the class. We have studied about half-wave dipole antenna, and when you studied the half-wave dipole antenna, we saw that if we take a lambda by 2 length antenna, if we take a antenna whose length is half wavelength, so once the frequency is fixed, we find out what is the wavelength, then half of the wavelength is the length of the material or length of the conductor that we are using as half-wave dipole antenna, and we are feeding at its center. Now when you design this, the conductor has a finite thickness. So assume that it is a rod, so it will have a finite diameter and it will have a length. So it will be like a cylindrical rod. The length of the cylinder will be much larger compared to its diameter. These are two things which are practical in nature. Now, when you feed this antenna, the length of this conductor is equal to lambda by 2. Then we have seen, based on certain assumptions, the assumption is basically the assumption is the diameter is negligibly small. Considering that assumption, we have seen that this antenna will radiate at a frequency which corresponds to its wavelength, half wavelength, which is the length of the antenna. So considering the length of the antenna is equal to half wavelength, whatever frequency comes out in calculation, with that frequency it should radiate, and at that frequency the input impedance, we have found out that the input impedance of the antenna will have a real part and a reactive part. The reactive part, if there is a reactive part in the input impedance, which means that there is energy storage. We do not want energy storage in the antenna. We want that whatever energy we are giving to the antenna should be radiated by the antenna. Why there is energy storage, or why there is a reactive part? So that part we have to understand and design the antenna accordingly. So that is point number 1. There is an energy storage. Because there is some energy storage, there is a loading, reactive loading on the antenna. Since there is a reactive loading on the antenna, that is changing its resonant frequency. So its resonant frequency will be something different from the designed resonant frequency. So to consider these effects, first is we must know why this is happening. Then we can use our own reasoning to decide whether how to compensate for these things. So look at the antenna as a transmission line. As we have discussed in the beginning of the antenna, we have said that why antenna radiates. We have said that we consider a transmission line, two-wire parallel transmission line. If we consider a simple two-wire parallel transmission line, that is not going to radiate. We have seen that the field between these two wires is tightly coupled between the two wires, so that field will not go out. The field just outside the two wires, the upper wire and lower wire, you see the figure here, the top figure, top left figure, the upper wire and lower wire, the fields are in opposite phase. Therefore, in the far field or at a distance, they will add up in opposite phase, which means they will cancel each other. So in there will be no field away from the two-wire transmission line. So theoretically this should happen, but practically there is a separation, so there will be some amount of negligible field. Anyway, now to make this antenna a radiating structure, what we do is we flare up the antenna at its end. So at the end of the antenna, so look at the graph that is shown, the inset in the graph. You can see there is a transmission line, and in the transmission line is flared up. So there is a horizontal line, there is a vertical line. The vertical lines, upward and downward vertical lines, are flared up regions of the transmission line. So the one is flared up in the vertically upward direction, other is flared up in the vertically downward direction. And that length, total flaring length, upward and downward, if we combine them together, then that is lambda by 2. So antenna, when we say antenna length is lambda by 2, or it is a half wavelength antenna, that is the total length. So total vertically upward length and total vertically downward length, if we add them together, that is lambda by 2. Which means each side, the vertically upward side and the vertically downward side, each of them has to be lambda by 4 or a quarter wavelength. Now if it is a quarter wavelength, suppose we have not flared it up, then what has happened? Look at the transmission line. If you look at the transmission line, and then from the open end, we go up to a quarter wavelength towards the input side of the antenna, towards the source side. The open end is the loading side, which is open. So load is open. Then you move towards the source to a quarter wavelength. Then at that point we open it up. Now if you move a distance on a transmission line, if we move a distance quarter wavelength, then at that point, at the quarter wavelength point, we get a input impedance which is of the form minus j z0 cot k into L. So that is the distance, that is the input impedance at a distance of quarter wavelength from one end. Here it is the load end. From the load end, if we move towards the source end, then it is this much, minus j k0 cot kl, if we have a open-ended transmission line. So in the open-ended transmission line, this is the wavelength. This is the input impedance. If we consider this input impedance, and if you take L to be lambda by 4, L to be greater than lambda by 4, if L is equal to lambda by 4, then Zin is equal to 0. So cot theta, cot kl or cot theta, kl is equal to k is equal to 2 pi by lambda, L is equal to lambda by 4. So 2 pi by lambda into lambda by 4, that is lambda by 2, pi by 2. So cot pi by 2, what will be cot pi by 2? Tan pi by 2, you know, tan pi by 2 is infinity, so cot pi by 2 is 0. So you will get 0 there. When it is lambda by 4, L is equal to lambda by 4. Cot KL is equal to 0. So Zin is as good as a short circuit at that point. Now what we'll do is look at if it is more than L is more than lambda by 4. If L is more than lambda by 4, then it will be inductive in nature. Because this will minus J Z0 cot KL will become positive. Now if it is positive, then Zin is equal to minus JXL in that form. So XL will be inductive in nature. If it is less than lambda by 4, then Zin will be minus JXC of the form minus JXC. It will be negative, so it will be in capacitive in nature. So if the length where we are clearing it up, so flared length is greater than lambda by 4, gives us inductive. Flared length less than lambda by 4 gives us a capacitive value. Flared length is equal to lambda by 4 gives us a resonating value. So because Zin is equal to 0, so reactive part is 0. If reactive part is 0, it is purely resonating. So that is what we need. Now why we are getting this lambda by 4 greater than lambda by 4 reason? Let us discuss why we are getting greater than lambda by 4. If you remember Zin expression, it is a real value Rin plus Jxin. Since it is plus Jxin, which means it is a positive value, it is inductive in nature. Means the folded up part is slightly greater than lambda by 4. Why it will be greater than lambda by 4? The reason is at the end of the transmission line, the field is actually fringing out, the electric field. So look at the second figure in the left hand second figure. So in the left hand second figure, you can see the fields are fringing out. Since they are fringing out, the length is actually extending. Physical length is L, but electrical length, because of the fringing fields, is extending. So it becomes L plus delta L. So since it is extending, we have chosen L. If we have chosen L to be lambda by 4 exactly, lambda by 4, because of the extension by an amount delta L, due to fringing field, the length now becomes slightly greater than lambda by 4. Because of the fringing, the length becomes slightly greater than lambda by 4. Since length becomes slightly greater than lambda by 4, it is inductive. There is an inductive part due to this fringing field. So inductive part comes into the input impedance. So it is not a resonating antenna. Pure resonance does not occur. It is reactive in nature. There is a inductive part. Now how to compensate for that? So to compensate for that, we should reduce L by an amount of delta L. So if L is less than delta L, less by an amount of delta L, then after the fringing by an amount delta L, and the total length will be L, total electrical length will be L, because now L is L minus delta L plus a fringing part which is plus delta L. So L minus delta L plus delta L will give us total A. Now that is assuming that the diameter has no effect. But when we look at the current is not only along the antenna, not only along the length of the antenna, current is also around the conductor. So current conductor has a diameter, so current is also around the conductor. Therefore, when we consider the length of the current, total length of the current or the total path traveled by current, it is L plus D, approximately L plus D. D is the diameter of the antenna. So what we will do is we will take L plus D to be slightly less than lambda by 2. If we take that L plus D is slightly less than lambda by 2, then the antenna will be purely resonating, because L is the length of the antenna, so length of the current, plus D is the path around the conductor, so that part is there. Then, so this is the total path of the conductor, and that should be equal to lambda by 2, but because of fringing field, it should be slightly less than lambda by 2. So when we design the antenna, dipole antenna, what we should do is, we should take L plus D to be slightly less than lambda by 2, or slightly less than 0.5 lambda. L plus D should be less than 0.5 lambda. Practically when we design, so this is important, practically when we design, we take L plus D to be approximately equal to 0.46 to 0.48 lambda. So somewhere between 0.46 to 0.48. Many a times we take 0.47 middle value we take. So L plus D should be approximately equal to 0.47 lambda. Then we'll be exactly, we'll get an antenna which has a negligible reactive part. Reactive part is almost 0, and which has a purely resistive part as the input impedance, which is resonating at the desired frequency. So start with this value. When you design the antenna, do a simulation. In the simulation, take this L plus D to be approximately equal to 0.47 lambda. Start with that. Then optimize the L value. D will be there. Then optimize the L value, or do a parametric study of the L value, so that the reactive part becomes 0 or negligible. So once you get that L value, then you design your physical antenna. So this is how to design a practical half-wave dipole antenna. This is the design consideration for a practical half-wave dipole antenna. When you design a half-wave dipole antenna, we will do this. Then next antenna that you have studied is the this antenna, the horn antenna. After that you studied the microstrip antenna. So let us consider the horn antenna. So now let me come to the horn antenna. For studying the horn antenna, you must have started with a normal rectangular waveguide. Let me tell you that I will concentrate on this in this discussion today. We will concentrate completely on rectangular horn antenna. We will not consider the conical horn antenna. We will consider only the rectangular horn antenna. Conical horn antenna you can study, or you can design accordingly. You can look at the websites that I will give you. So you can look at the websites. I will intimate you which website to look for. Now, on the portion that I am going to discuss is actually taken from the NPTEL website, in which you can visit the NPTEL website. In that you can see the lecture by Professor Girish Kumar. Professor Girish Kumar of IIT Bombay. So look at his lecture. That is very informative for practical antenna design. From practical antenna design point of view, his lecture is very informative. You can look at his lecture on NPTEL about the horn antenna. I will just try to summarize what he has mentioned in his lecture there on horn antenna. I will try to summarize it mostly in today's discussion. So it starts with the horn antenna actually is basically a modification of the waveguide. So you have a waveguide which is feeding the horn antenna, and we consider the waveguide, we consider a rectangular waveguide. The breadth of the waveguide is A, breadth or width
of the rectangular waveguide is A, which is along the usually we call it along the x direction. So if you have the coordinate system, in the coordinate system, the line which is describing the breadth or the width of the antenna, that line is along the x-axis. The height of the antenna, that line is along the y-axis, and the line perpendicular to xy plane is the z-axis. So along the z-axis there is propagation, along the x-axis and y-axis the extension of the waveguide is there. When you consider waveguide, then in the waveguide, you know, the dominant mode is the TE10 mode. Now TE10 mode means the mode 10 that we have discussed earlier in the electromagnetics class. 10 means half wavelength variation along the x-axis. 1 represents 1 half wavelength, 0 represents 0 half wavelength. So along the y-axis there is no variation in the electric field. Along the x-axis there is 1 half wavelength variation in the electric field. And there is 1 half wavelength variation along the half wavelength variation of the electric field along the x-axis. Now TE10 mode means the electric field is not electric field does not have a z component. So electric field will have only y component. It does not have a z component. Since it will have a y component, in the TE mode, TE10 mode, the electric field EY, y component of the electric field, that is varying along the x-axis only. So EY is a function of x. It is not a function of y because there is no variation along y. N is equal to 0, m is equal to 1. So EYX is equal to E0. E0 represents the amplitude. So there will be different values, all constants. So if you take all constants together, that gives you the constant E0. So it is E0 gives you the amplitude into cos pi x by a, or cos pi by a into x. Now how do you justify this? You must have studied, you have studied it in the waveguide, how to justify this. Now you can see it is varying along the x-axis. At the two ends of the x-axis, the value of x is equal to 0, value of x is equal to minus a by 2 and a by 2. At the center we have at the center of the waveguide we have the origin of the coordinate system. So from the center towards the left, so towards, if you look away from the paper, away from the screen, then that is along the minus x-axis. So at the end, away from the screen, at the end, you will get x is equal to minus a by 2. Similarly, into the screen, at the end, you will get x by 2. Now, when you are at the center, when x is equal to 0, then cos pi by a into 0 is cos 0, that is maximum. Now look at the field distribution. At the center, the field is maximum. Now come to the end. At the end, we have an electric wall because it is a pure conductor. So at the end, both the ends, it ends in the pure conductor electric wall. Now if you have electric wall or a pure conductor, on a pure conductor, electric field is 0. So output x is equal to plus minus a by 2. This will be cos of plus minus pi by 2. Cos of plus minus pi by 2 is equal to 0. So at both the ends, it is equal to 0. So this form justifies that the field distribution. So Ey is equal to E0 cos pi by a into x, and this gives you 1/2 wavelength variation. At one end it is 0, then it goes to the maxima, gradually increases
in a cosine distribution it goes into the maxima, then it comes down to 0. So this is 1/2 wavelength variation. So this is how the field is distributed on the aperture of the waveguide. Now this aperture is expanded. After this, for the horn antenna, this aperture is expanded. So I will see how to what happens when you expand this aperture. Okay. Next is, let us see the expansion of the aperture along the b-axis, now or along the y-axis. The aperture is expanded, or aperture opens up along the y-axis. So at a distance from the waveguide, so you come to a distance maybe r or rho, so come to that distance, then there we have expanded the aperture. So aperture expands at the end, so you can see at the end we have the aperture expanded. If we have the expanded aperture, then it becomes the aperture on the waveguide was a cross b, so length was so width was a, height was b. Now the expanded, in the expanded case, expansion is along y-axis, therefore that becomes b1. B has been expanded, so b becomes b1, but a has not been expanded, a remains constant, so a becomes a. So a is not changed, so a becomes a small a, but b becomes b1. So in books, many books you see it is a, b1. In many other books there will be other symbols. Here what we will do is, for b1 we will write capital B also. Sometimes we will write capital B. Towards the end of our discussion, for b1 we will say capital B. Similarly for small a1, here a1 is equal to small a, because that has not changed. But if a changes, small a changes, then that we will call capital A. So small a is equal to small a1 is equal to capital A. Now because of the flaring occurs angularly. There is a angular separation. The aperture opens up, which means it is there is a angular separation. So from the center axis, which is the z axis, from the z axis we move towards the y axis by an angle. In the upward direction it is psi, in the downward direction it will be psi, so by an amount psi. So that is what it occurs. So z does this. You can see the coordinate axis here. The expansion is this. Now if it is expanded, then what we do is, maybe in the next slide I will show you that. That will be better. So let us take a side view of this horn antenna, E-plane sectoral horn antenna. Let us take a side view. In this side view, what you can see is that the horn is there. Before the horn there is the waveguide. We are looking at the side view. So the height of the waveguide we can see. Height of the waveguide is b. That comes. Then B starts expanding. So if B starts expanding, it expands. After expansion, B becomes B1. Total is B1. So if I draw a horizontal line here along the z-axis, then from the z-axis down to the bottom of the expansion is B1 by 2. Similarly, up to the bottom of the top of the expansion, it is B1 by 2, total is B1. So that you can see at the end. Now, if you look at this, then you do one thing. From the expanded points, from the top point and the bottom point, the line which joins the waveguide, that line you extend into the waveguide. So from the top point, come to the waveguide, extend it into the waveguide. From the bottom point, come to the waveguide, then I extend that to the waveguide. Then those two lines, you can see in the figure, there is a dashed line which is the extension. The dashed line of these two edges, they will meet at a point within the waveguide. That point, if you look at that point we call the phase center of the E-plane sectoral horn antenna. That is the phase center of the E-plane sectoral horn antenna. Now from the phase center, if you draw a radius take a radius up to the face of the waveguide, which is rho 1 or R0, capital R0 or rho 1. In some books it is written capital R0. So after this slide I will show you capital R0 or rho 1. So from the center, if you draw take a radius up to rho 1 or R0 and draw a sector. So the dashed line that you can see is a sector. And now on this dashed line, if I consider this dashed line to be the phase front or the wave front, then on this dashed line, the phase of the electric field is constant on this dashed line. Why it is constant? Because my source to this dashed line is the phase center. From the phase center, if the distance onto this dashed line or dashed curve, everywhere it is same, because it is the radius, so radius remains constant, therefore everywhere it is same. So that is the phase front or the wave front of the wave propagating inside the structure. So inside the waveguide, then inside the conical expansion or inside the sectoral expansion, the wave front is same on the dashed line portion. But if you move away from the dashed line onto the face of the waveguide, there is a path difference as you move from the center point of the face to the edge of the face. So at the center point there is no path difference. The center point and R0 or rho 1 are the same point, so there is no phase difference. But as you keep on moving towards the edge, there is a path difference, and you know the path difference gives rise to a phase difference. So as you move towards the edges, there will be a phase difference. So the electric field which is propagating in the z direction will have the distribution on this face, on this aperture or on this plane will be of the form Ey, that will be there, which is E0 cos of pi by pi x by lambda or pi by lambda into x. That will be there. That into the propagating value. Propagating value will be along the z direction, so that will be exponential minus jkz. So in that form, that will be there. That will see. That you must have seen already. So I'm not going to repeat it, but I am just telling you. So that part takes care of the phase. When you consider the z part, the propagation along the z path, that must take care of the phase part. So we'll see that. So this is about the E-plane sectoral horn antenna. Then we'll consider the H-plane sectoral horn antenna. In the H-plane sectoral horn antenna, the height B remains constant. Height B does not change, but the width changes. Since the width changes, width will keep on changing. So the expansion is along the A or along the x-axis. Instead of expansion along the b-axis, expansion is along the a-axis or the x-axis. Instead of y-axis, expansion is along the x-axis. When expansion is along the x-axis, then it looks like this. If I look at the waveguide or the horn antenna, the H-plane sectoral horn will look like this. In this case, at the face of the horn or the aperture of the horn at the face, there because of expansion, B does not change. B remains constant, so small b remains constant, so small b will be equal to capital B. But A has changed to A1, so small a now becomes small a1 or capital A, either of these two. Then other things remain same. Expansion angle is angular separation is psi. So by an amount of psi we have expanded. So then you can see, as in the previous case, we can also consider why there will be a phase difference. Here also you can see the phase point. Phase center is due to the dashed lines. They meet at a point, that is the phase center. Our center of the coordinate system is the phase center. So let me not show you. Let us not see the diagram. That is not necessary now. We have seen that diagram for the E-plane sectoral horn antenna. For this sectoral horn antenna, we will not see the diagram. It is similar as in the previous case. Now after this, we have seen that we can expand along the x-axis. The face of the waveguide can be expanded along the x-axis, or it can be expanded along the y-axis. Either of the two axes we can expand it. If we can expand in either of the two axes, we can expand in both the axes. If we expand it in both the axes, then what we get is called a pyramidal horn antenna. In this case, both A and B changes. If A and B changes, this will be A1 and B1. A1 will not be equal to A, B1 will not be equal to A. So you can say A1 is equal to capital A, B1 is equal to capital B. So this figure we have taken from Professor Girish Kumar's notes available on the NPTEL. Similarly, we can see that, so now on that we discussed this. Okay, we can see that there can be three types of rectangular waveguide. One is called E-plane sectoral horn antenna, one is called H-plane sectoral horn antenna, one is called pyramidal sectoral horn antenna. In all the cases, the electric field is oriented along the y-axis, so we have the EY component. On the aperture of the horn, EA, which is the electric field, that is always oriented along the y-axis, because we are considering only the TE10 mode, the dominant TE10 mode. That is what is we are considering. The horn antennas are designed in the dominant TE10 mode. So always the electric field, when you go to the design of the horn antenna, they will be along the y-axis or along the breadth of the along the height of the aperture. So not along the breadth of the aperture, it will be only along the height of the aperture. Along the breadth, it will remain constant. Along the breadth, the variation will be cosine variation. So there will be cosine distribution along the breadth, but along the height it will remain constant. So with this, we'll take a short break. Then we'll come back and discuss about some practical aspects, some more practical aspects. Those we will discuss after a short break. Let us take a short break of 5 minutes here.